So in the remaining lectures I will give an overview about how to find general curves. So maybe the easiest way to define a curve is as a plane curve, just as a plane curve. Now, so if we have plane curves, so every smooth projective curve can be projected into the plane, and under a general projection it will get a finite number of nodes. So, so we have C is C prime in P2. This is birational. The degree of C prime, say, is D. Then we can compute by the genus formula of plane curves the number of nodes. So the genus in general is D minus 1 choose 2 of a plane curve of degree G, D minus 1. So the difference between these numbers is going to be delta, here the general, say, projection, or morphism, and then we have delta nodes. So to answer the question, which kind of curves can we easily write down as a plane curve, we should answer first the question, how many maps to the plane up to projectivity do we have on a given curve? So let me recall a little bit of Brill-Noether theory. So see a curve, then pick D of C, the line bundles of degree D, L, a line bundle of degree D. Then we have the Brill-Noether loci WRD of C, which are line bundles L, and pick D of C, so they have degree D line bundles such that H0 of L is at least R plus 1. So given such line bundle, we at least get a rational map if you choose R plus 1 dimensional subspace. So above this we have the space GRD C, which is sort of tuples tuples L comma V, such that V is in H0 of L in R plus 1 dimensional subspace. And given this, given L and V, we get a map Phi-V from C, a rational map, into P of V by picking a basis. So V maybe has a basis F0 up to Fd. Then we send P, point P, to the ratio of R of P. And it's embedding, it is a morphism, sorry, not embedding, a morphism. If V is base point free, linear system V is base point free. This will, okay. So to answer the question is we would like to know which WRDs are non-empty, and the condition is if C is the general curve. First statement is the so that L be a line bundle which has on C which has precisely R+1 sections. So I take a point like that. Then the codimension of at the point L of WRDC inside pic D is less than equal to H0 of L times H1 of L, which is R+1 times now by Riemann-Roch. We have H0 of L minus H1 of L is equal to the degree of L plus 1 minus G. And so H1 of L is G minus R plus D. So the codimension is as most this, and the second statement if C in the moduli space MG of the general curve, if C in MG is general, then WRDC is non-empty if and only if rho of G RD, which is defined to be G minus R plus 1 times G minus R plus D, is non-negative. In that case, WRDC has dimension rho, and so okay. And then there's one further piece of information which I just want to mention. If rho is larger than 0, then WRDC is connected. So the first statement is due to, so I give some references. The first statement really is due to Brill and Noether. The second statement is due to Griffiths-Harris. And the connectedness result is due to Photon-Lazarsfeld. So, for plane models, general curves on a general curve. We need d such that g minus 3 times g minus 2 plus d is greater equal to 0, which is equivalent with what? Did I do this? It's I got this number wrong. Plus r minus d, and everywhere else also plus r minus d. So this it was supposed to be h1. So h1, if I bring it on this side, h0 was r plus 1, so here I have an r, so r minus d, g comes on that side. So g plus 2 minus d is greater equal to 0, and that means that d should be larger or equal to 2g minus 6 divided by 3, and then I should round up. Right? So we can hope to find a plane model, which presumably will only have nodes of degree d if d is at least these numbers. So Schreyer used this to prove that mg is unirational for g less than equal to 10. So a general curve of genus 10 or less can be written down as a plane curve by choosing 3 parameters. I'm going to choose 3 parameters. So how does it go? So so unirational means that I have sort of can write down the family of curves, or a dominant family of curves, depending on 3 parameters, right? Independent parameters. So the idea is, for example, let's take g equal 10. Then what is the degree? 2g is something is, I did this computation right? D is 4, that's way, this is way wrong. Here's a plus sign, that makes a difference. So 16 divided by 3, so it's 26 divided by 3, so I should choose a model of degree 7, right?
That's opposite.
Let's see, so
something.
G for 10. So 20 plus 6, 26 divided by 3 is 8 and a little bit,
Yeah,
so, and it should be 9. So D should be 9, and then I have a choose 2 minus 10, which is 18. Is this correct? A choose 10 is 4 times 7 minus 10 is 18 double points. All right.
Yes.
And so Now, in general, very, very little is known about the position of these double points. So in the construction step, I'm going to choose the double points freely. I choose (18) general points. And then we ask whether the H0 of the ideal sheaf of the points gamma, P1 up to P18, ideal sheaf of gamma in degree 9 is non-zero, right? Because we want the gamma ideal, I need a double point so that it's the ideal sheaf of gamma squared. 9. And this has, of course, an expected dimension. The expected dimension is forms of degree 9, so it's 11 choose 2 minus 3 times 18, because imposing a double point is one condition for the position and 2 conditions for the tangency. So this should be singular, right? So let's see whether I got the numbers right. So this is 55 minus 45 is equal to 1. So if I choose general points, I will expect that I can find such a curve, and the curve will be singular. We'll have only nodes now. Check that for general choices. Of the points, equality is true, so H0 of this equality holds, and the corresponding curve has nodes only, is smooth outside, smooth, reducible, is let's say is has nodes, has singularities only in gamma. These are nodes, these are ordinary nodes. And it's reducible. At the time of Severi, this is a pretty obvious statement that it should be true, but it's not completely clear that it actually is true. To assure that this is true, it would suffice to compute a single example. Now, at the time of Severi, this would be a difficult thing. I mean, choosing 18 points is really a lot of equations. And to compute these things is sort of it's a big computation if you do it by hand. But this is easy by computer. Easy by computer. E.g. using Macaulay. There's a very short program which sort of checks this. Now I should choose general points. How do I choose general points? Well, actually I would prefer to go over to a finite field, to work over a finite field. Then clearly I can choose the coefficients of the points at random. And this will define a random collection of points. I choose a coefficient in the ground in my finite ground field at random. then the curve will be defined over this finite field. And then I can check whether that curve over this finite field has all this property. And then I argue by semi-continuity. So if I choose a finite prime field, then I can view the coordinates of these points over this finite field as a specialization, as the coordinates defined over the integers. Reduced mod p. Mod. Right? So every computation here can be seen as a reduction of a computation mod p, of a computation which I could in principle do over an open set of spec z. So maybe I have to invert some numerator. So maybe this works over z 1 over b. b an integer which doesn't, which is co-prime to my favorite prime p, which I choose here. So this is going to be easy. Now what about the next case? What happens with 11? So if g is equal to 11, we go back to this equation. So the 22 plus 6 is 28 divided by 3 is a little bit more than 9. So now d is 10, I believe. And so I get 12 choose 2 minus 11 double points, which is 55, I guess. Is this correct? 6 times 11 minus 11, 55. And then H0 of I of gamma of D is 10. No, this was wrong. D minus 1, 9, choose 2, 45, minus 11 is 36. Double point, this is correct. I can't compute very well. 9 times 4 is 36 minus, I should do it slowly. So this is 36, you agree with me? Minus 11, which is going to be 25, right? Now I have to compute this dimension, the expected dimension of this. So it's 12 choose 2, which was this 55, minus 3 times 25, and this is negative. So the conclusion, and you can check this by example, the points have to be in special position. Have to be. Because if they're in general position, then I won't find.
How to count either square root number?
Well, each point imposes 3 conditions.
Yes. So
Right.
2 times divide.
Yes.
How about 12 choose 2? 12 choose 2.
12 choose 2 is 66. I'm sorry for that. So 66, it's still less than 0. Quite a bit less than 0. Right? So I have to, these points have to lie in very special position. Okay? So the points have to lie in special position, and what kind of special position? Well, nobody really knows. The condition is presumably that this space here, that this space is non-empty, which is then sort of a tautology, right? I mean, that's not going to help me. If I would be able to say in a different way what kind of condition these points should satisfy, then it would be better off. But they don't. I don't know that. So that's why Severi could do it for G less than equal to 10. Nevertheless, Severi at that time conjectured that all the moduli space MG are unirational, based on this result maybe as a motivation. And this then was proven to be wrong. So we have Harris-Mumford. In the early 80s, they proved MG is of general type for G larger than equal to, well, G equal 22 or G larger equal to 24. So maybe that's also a contribution of Eisenbart. Harris. So general type means that the canonical bundle on the compactification of Mg, a desingularization compactification of Mg is big, has sort of many sections, which in turn means that in Mg there is no point curve through a rational curve through a general point, which in turn means if you write down the equation of a general curve in some projective space, so it's given by some equations, and you want to write down a family, so a one-parameter family, then you have to vary the coefficients, right? And what this result says, that none of the coefficients, the essential coefficients, varies freely. So they all depend in complicated algebraic relation on each other, and you have to solve a big system of algebraic equations to do that. So there's no way to let one of the parameters depend in part be free. So it's sort of quite opposite on a unirational variety, which by definition means that there's a projective space Pn and a dominant map, Mg X dominant rational map. That is by definition X is unirational. We can connect any two general points here by a rational curve by taking P images here and taking a rational curve in this big projective space and take the image. So this is very different from general type. On general type varieties, we do not expect that there are many rational curves on the variety to start with, certainly not through a general point. So
what algebra Harris did again?
Harris and Mumford did the, I think they did the odd genus case first, looking, and then Harris and Mumford did the even genus case, and at the moment we know that for 23 we know that's non-negative Kodaira dimension, which is sort of a weaker statement, but in general we're not going to be able to write down a general family with 3 parameters. So this was in the 80s. I think this started in 1982, I believe, with 1988 or something, 89, maybe a little longer period of that. And then later Farkas picked up this topic and came back to it and improved many results. Well, if we can't construct the curve, a model of the curve in P2, maybe we should try to study the curve as a curve in P3. So models in P3. Here, of course, I need then correspondingly that D3 is greater or equal, well, I need G minus 4 times H1 is greater or equal to to 0, right? So H1 of L. So a tempting case is actually G equal 12. This was done by Zanesi. Or G equal 11. Which and 13, which was done by Chang and Brown in the 80s. So they basically, when Harris and Mumford got the result, they immediately tried to improve upon Severi's result because it was very tempting, because there are finitely many more cases to study. So the question is, how do we describe curves in P3? And here the crucial role is played by the Hartshorne-Rao module. So the role of the Hartshorne-Rao module. So if C in P3 is a curve, we have the ideal sheaf of C, O of projective space, and O of C. And on global sections we get sort of H0 of O P3 twisted by N going to H0 of O C of N. In this map may or may not be surjective. The kernel is the ideal H0 of the ideal sheaf in degree n. And the co-kernel is H1 of IC of n, and then we have 0. Right? So IC, the ideal, the homogeneous ideal, is the direct sum over the H0 of IC of n, and greater equal to 0, so homogeneous ideal. And the direct sum of the H1 cohomology which is commonly denoted by H1 of I star n, H1 lower star IC, is called the Hartshorne-Rao module. Is the Hartshorne-Rao module. So of course there's a very good reason why this module is called Hartshorne-Rao module, because Rao proved that this module up to twist characterize liaison classes of curves. So and maybe I go on and talk about the free resolution. So we have SC, which is a quotient of the polynomial ring. So S is going to be S is the coordinate ring, homogeneous coordinate ring of P3. And then there will be a free resolution, and it will stop at position 3 at most, because SC is has depth at least 1. If SC is Cohen-Macaulay, then F3 is equal to 0, and the complex F1 and Fs, F1, F2, we have that the rank of this here, this is a graded free module, so it's a direct sum of S minus AI, and this is correspondingly a direct sum of S minus Bj, and the rank should add up, so the rank of this complex, the alternating sum of the ranks, should add up to 0. So this should be, maybe I run here from I equal to 0 to R, and here from J equal 1 to R. So this matrix phi, the matrix phi ij of homogeneous form is R plus 1 times R matrix of homogeneous forms. Phi ij is homogeneous of degree AI minus Bj. Now, at this point, we have an important structure. Right? We have the Hilbert-Birch theorem. It says that the first map here, delta, the first map delta is given by a row vector, delta 0 up to delta R, where delta I is equal to minus 1, because the I is the determinant of the matrix phi ij, phi Lj, where L is not equal to I. So I drop the else row. And takes a minus. So any such short complex, here it's given by a matrix of forms. This is also given by a matrix of forms, but these here are really just the minus of this matrix here. So delta phi define the complex. How to see this? Well, and you have to prove that delta I times some I equal 0 to R times phi ij is equal to 0. And what is this really? Well, I can take the matrix phi 0j up to phi rj, and then phi 0, 1, 0 j runs from 1, so phi phi 0j up to phi rj. R1, sorry, going to phi 0 r up to phi r. So I look at this matrix. So I have repeated one of the rows, one of the columns, sorry. And now if I do Laplace extension of this here, if I compute the determinant of this, then of course it will be 0 because I have repeated a row. But if I multiply this and do Laplace expansion, then I multiply this entry with the matrix delta 0. So it's precisely this expression. So delta phi do define the complex. I compose to 0, and then it has to be has to prove a little bit more that this is sort of basically the only choice I have. I can multiply, of course, this delta with a common unit. I could do that. I mean, it doesn't change the complex really. It's just an isomorphism here. But up to that, this is sort of makes it unique. So the key point here is if I have a sufficiently general R plus 1 by R matrix, then the minus will define something in codimension 2. And it's sufficient if the degrees are nice, so if they have all positive degrees, and I choose general matrix phi, then actually the variety defined by delta will be smooth in expected codimensions. Singularities will occur in codimension 6, in generally speaking. So it's easy to write down codimension 2 spaces. Now, this being short is equivalent that C is Cohn-Macaulay, which is equivalent. So this is also equivalent that H1 of the ideal sheaf of C is equal to 0. So the Hutchin-Rao modulus 0. So what happens if the Hutchin-Rao module isn't 0? So if H1 star of IC is not 0, then still we have sort of, we can sheafify, so we have a sequence OC with O, with a sheafified F1, sheafified, and the kernel of this, because C has codimension 2 in P3, and P3 is a smooth space, this will be a vector bundle.
What is P3?
A vector bundle, the kernel.
What is F3?
If F3 is 0, then this bundle would be the sheafification of F2.
Yes.
Right? And what about this bundle? What's the cohomology of this bundle? Well, these are direct sums of O's, right? This here is the direct sum of O minus AI, right? So they have no middle cohomology. So there's no H1, no H2. So H2 lower star of G, the H2 cohomology, is going to be the same. Here I have the deal sheaf as the H1 cohomology of IC. Right? Here I have IC in between. And what about the H1 cohomology? Well, this map is surjective on H0 in all twists. And so the H1 cohomology goes to the H1 cohomology here, which is 0, and the kernel is a co-kernel of this map on global section, and H0 star and H1 star of G is equal to 0. So now what is liaison? I can take equation Fg in the homogeneous ideal of C and take Fg, zero loci. This will be C union an additional curve E. It will certainly contain C if I take two here general. And then two surfaces in P3, they will intersect in a curve. One of the components is C. There might be a different component. So the right way actually to define is IE is equal to, and now I take the ideal generated which way is it? I take a function which vanishes here, multiply with a function which vanishes here, and it vanishes on the union. So it should be the ideal generated by Fg colon IC. So that's sort of the right definition of IC. So this is all the function which, if I multiply any function, any element in the ideal of F, I end up in the intersection. So this is the correct definition. This here is a little sloppy because in principle could be that the two surfaces, surfaces F and G touch one another in long front C. So it could be that E and C have a common component. Now if I take this definition, I only need that F and G is a complete intersection. So I have my O, I have here direct sum of line bundles, O of minus AI, and then I have my bundle G on one side. On the other hand, it is a quotient of O of the complete intersection, which is X. So I call this X, which is O, and then you have O of minus D times some O of minus E, and then with the causal relation I get sort of O of minus D minus E. This is a causal complex. So to say that the equation of F vanishes on C means that I can write it as a linear combination of the defining equation of IC. the homogeneous ideal. So this was supposed to generate the homogeneous ideal. So I can write the equation F as a linear combination of those generators, and similar to E. So this will give me that map, and I have G here. And I get sort of from this diagram induced map here. Now apply the functor hom omega p. Omega p3 to this diagram. Of course, these are torsion sheaves. So if I dualize this diagram, so I get a diagram omega, I get here omega p3 equal omega p3. Well, omega p3, maybe I should write this as O of minus 4. So then here I get a map to diagram O of ai minus 4. Here I have O of d minus 4, diagram O of e minus 4. And the map now goes in this direction. Here I get sort of G dual twisted by minus 4. And then by duality theory, here I get an X group. So this is sort of the X, this is a resolution of OC, locally free resolution. I can compute the X sheaf X 2 on OP3 of OC with values in omega p. And similar here, here I have another term, O of d plus e minus 4. The map goes in this direction. And here I have omega of the complete intersection, which actually is O of x d plus e minus 4. And the map goes in, what is wrong with this map? This goes in this direction. On the other hand, I can look at the sequence OC, OX, and the ideal sheaf of C in X, and apply X there. So here I will get X2 of the ideal sheaf of C in X with values in O of omega p. Now, which of course is a sheaf supported on E. And it's a cyclic sheaf. If I twist this back by d plus e minus 4, so if I twist here back, I get a resolution. So this is going to be put in the twist. This will be O of E twisted by d plus e minus 4. And the mapping cone over this sequence is going to be a resolution of E. So what we get is that we have a resolution of E. So we have OE we have this copy of O, P3. Then we have G dual, and I should twist back by this twist here, so I get G dual. Twist it back by minus D minus E. And then I get sort of this direct sum with this term here. Which is of minus E direct sum of minus D, right? And then finally I get this term here. These two terms cancel, so the map was in the other direction. These two cancel out if I go to the minimum resolution, because an isomorphism. So, and then here's the direct sum O of D AI minus D minus E. And there's a map sort of going both in this. So have a resolution like that. So H1 star of the ideal sheaf of E will be H1 star of G dual times D minus E, which by Serre duality is the same as the H2 lower star of G. And now the twist go the other way, D plus 4, D plus E minus 4. Dual, which is the same as the Hartgen-Rao module of C, dualized. So this is finite dimensional vector space. I take the dual vector space. This is a graded vector space, and I have to twist out by this D plus E minus 4, which is H2. So which will be so the minus 4 is the canonical. I leave this here. It's sort of twisted by D plus E minus 4. I twist this module. Right? So the Hartgen-Rao module of C and E coincide bis auf duality and shift in degree. Right? If I do it twice, I get back a double dual, I get back the original module. So Rao's important theorem H1 IST of C characterizes the even liaison class. The liaison class of C. So I did liaison once. So I had here C, I linked with F and G to E. I can do it with a F prime, G prime to some C prime. Then C prime to C is in is an even linkage. I can repeat. I take the transverse flow under this generated equivalence relation. And we say that two curves are in the same even liaison class if there exists a chain of even links. So I do always 2 steps, another 2 steps, C double prime and so on, which connects one curve with the other. So that's the even liaison class. And Hartshorne's Rao's important theorem is that this module, this finite length module, up to twist, characterizes the even liaison class of C. So I will tell you what will be next and then stop. So next I view this result in such a way that basically the difficulty to construct a curve lies more or less entirely in the difficulty to construct a module, this module of finite length with the right properties. So constructing modules with finite length, which at first seems to rather ungeometric object, but very algebraic, is the equivalent to construct the curve C. So the step to how to get from the Hartshorne-Rao module to the curve. Well, basically, you see, you have this here. Right here, we have a vector bundle. Here we might act. So this vector bundle is basically determined by its middle cohomology up to direct sum of line bundles. So we have a vector bundle plus possibly some direct sum of line bundles. And then we have to choose the right number of sections of that line bundle, form a bundle version of the Hilbert-Birch matrix, R by R plus 1 matrix, and take then the ideal generated by the minites, which make perfect sense as an ideal sheaf, and get back the curve. So that will be the strategy to construct space curves.
Can be connected to the unidirectionality of some.
Yes, I will use this construction to prove this unirationality for genus 12, 11, 12, setting to prove Chang-Ran's results. Okay, and I will do a little bit like that next time and show you where sort of this stops to work. I mean, why doesn't it work in general, right? I mean, there must be some difficulty, and the difficulty is not so much the construct, how to pass from the Hartshorne-Rao module to the curve, but rather the difficulty to construct the Hartshorne-Rao module in the first place. Okay, so that will be the content of the next lecture.
Okay, then we continue on Friday with David.
Yes, on Friday there's David. Yeah. So, but next week.
Maybe it's fine.
Or Friday, whatever you want.
Okay, I will make a scheme.
Okay.
Okay, thank you very much.